All right, I just want to talk a little bit about ROP and texture. I'm not going to go through any of the details of what's improved about them. And I can go through a little bit. Just basically show some performance numbers. GT285, going from 8x to 4x to 8x AA would cause a significant perf drop, something like 40%, which was disconcerting. We did many things in our design, many things in the ROP to improve the performance. So 4x did get faster than GTX285, but also going from 4x to 8x shows a very small drop in performance. And as you can see, it's a very big increase in performance versus where GT200 has. So basically our 8x AA performance has increased greatly, probably due to some of the things we did in the ROP. Any questions on this? Okay. On the texture side, we've also done a lot of things inside texture to make it more efficient. So we've got about the same texture horsepower, speed of light texture horsepower as GTX285. But we've done things to make sure that we were running at the speed of light as often as possible. And so as you can see by these are also state buckets, as Henry described before, but they're different apps when they're texture bound. And so Left 4 Dead in this specific bucket got 40% faster, Crisis got almost 80% faster. Lenticular Halo and 3D Mark Vantage got about 60% faster and so forth.
And just to be clear, right, the speed of light is just our term for maximum efficiency.
Yeah. Speed of light is peak performance.
Just so you know that.
Yes. Can't go any faster.
Yeah. Okay. Anyway.
Okay. So, any questions on the architecture before we go on to some of the things we did to improve image quality? Okay. All right. So shadow buffering is the common way shadows are done currently. There are some people still doing stencil shadows, but most all of them are doing shadow buffering by rendering from the viewpoint of the sun or the light or whatever, the scene, and then seeing how it intersects with real objects to determine if it's in shadow or light. And what ends up happening is traditionally apps would do one texture fetch, do one comparison, and generate an inner out versus the shadow. And you'd see these artifacts, where you'd see these jagging lines on shadows, which is noticeable, and they crawl all over the place, look horrible. So a few years ago, developers started doing things where they'd sample each shadow map multiple times per pixel in a jittered format in order to blur out these effects. And that goes on to the next picture. So as you can see here, these shadows look nice and smooth. You don't see any of those jaggies and so forth. So that's what developers started to do. Now the problem there is you end up spending a lot of time generating shadows. In fact, I think this was from 3D Mark 06. It spends like 30% of its time or more in the frame just generating shadows. And still it doesn't look good enough. You really want shadows for multiple lights, and with more geometric complexity, everything else gets a lot more complicated. So we did a few things to improve our shadow buffer performance. One of which was by increasing geometric throughput, we were able to render that Z-only scene from the sun or from the light source a lot faster, because it's usually primitive rate bound. The other thing we did is we put in this mode that's supported by DirectX 11, where one texture fetch can fetch 4 pixels that are offset in not random ways, but offset are specified by the application. So you can actually basically do one texture instruction that fetches 4 jittered samples. And the range of the offsets is between 64 and minus 64 and plus 63 pixels. The data can either be, we've got a mode in the texture unit where we compare against the Z-value given or from the shader to determine whether it's in or out of the shadow, and then the results average and pass back. We also have a mode where we pass all 4 pixels back to the shader, and it can do whatever it wants with the pixels. We're seeing right here, there's a substantial performance improvement by doing this. We took one of the Microsoft SDK samples and added jittered sampling to it, and then enabled this mode. And for our hardware, got 2x faster by going to this jittered sample mode versus doing it by doing 4 separate texture lookups. From what we see versus ATI, we're seeing about a 3.3x performance improvement. So this is a very important thing. We're listing it under image quality improvements versus performance, because the faster you can make certain capabilities, the more developers will use them to increase image quality. And shadows and lighting is one of the key areas where we need more image quality improvements. Next. Okay. So let's talk a little bit about the way people do some things which look like geometric realism now, but aren't quite real enough. This is a scene from Age of Conan. You've got all these grass blades, and ideally what you like to do is render them all as multiple triangles. there's a few problems with that. The biggest of which is there's way too many of them. The performance falls off the cliff. There's other issues with translucency and other things, which means you have to generate a pretty decent pixel shader in order to get the grass to look really good. But so what developers are currently doing is they do something called a billboard, where they take a flat quad and they paint on it a bunch of grass or a tree or whatever. Anywhere where it's not the grass or a tree, the alpha value is set to 0 or transparent. Then ideally what you like to do is alpha blend them all together. So you've got these multiple billboards, there's multiple layers of grass. You can animate them by distorting the billboard and so forth. But you put on multiple layers of grass to basically give you this thing that looks like a field of grass that's waving. It looks really pretty. The problem is if you alpha blend them all, now you have to sort them all from front to back or back to front. You can't just randomly generate them. That doesn't work because you become way too CPU limited doing that sort. So what developers do is they do, in alias mode, they do something called alpha test, where they basically look at the output of the pixel shader, and if the alpha value is below a certain threshold, they just kill the pixel. If it's above a certain threshold, they render the tree, or render the pixel. And that ends up with the blades of grass look okay, but they kind of have this really sharp edge on them. And as you move in, as things move, you can see the edge crawl all over the place. So what we've done before is we've done something called alpha to coverage. This came out on G4 7800, which in anti-alias mode, instead of doing an alpha test, it uses the alpha coming out of the shader to turn off selected numbers of samples depending on how, what the alpha value is. That allows the edge to look smoother because you get some sort of transparency as you move along. So we've done some things to increase the image quality of basically the alpha test, or alpha coverage mode. And where the little rectangle was on the previous screen, we'll show you some images of what it looks like. So we've had this mode since G80 called CSAA, which allowed you to have not only full coverage, but full samples, which have color, Z, and basically coverage. You have these bits that just specify coverage. And what that allows you to do is that allows you to have more smooth edges, basically, on lines like shown here. Even in this one here, for instance, it shows 32 levels of transparency, or transitions here, even though we have 8 full samples. So these extra coverage bits allow the edges to look a lot better. And we've done that. Our current solution that we're shipping, best we have is 8 real samples, 8 virtual samples. So we've done some things to actually let it improve alpha to coverage geometry. We'll get to that in a minute. We'll also go a little bit over what CSA looks like, or how it behaves. Next slide. So the thing we've basically done for CSAA, you've got these real samples, which are scattered all over the place in a given pixel, and then you've got these virtual samples. And each virtual sample has up to 3 bits that say which color it's associated with, either that guy, or that guy, for instance. And then as you render it, polygons come through and slice an edge, and some of those may get disconnected. And the coverage bit basically will get its color from whichever ones are remaining. That allows, for instance, an edge that cuts through here will have more coverage for some of these samples than it would normally get. So that's kind of the way it works. When we do the resolve to go from multi-sample to single sample, we look at those coverage bits to figure out how to weight the full coverage. So like I said, this was introduced in G80, and we've done some significant enhancements in GF100.